Hey guys, live long and prosper.
Hey, Marisa.
Hey, Marisa. What do you got held up there?
Well, I heard that we were having like a volcanologist on the show today, and so I just wanted to be respectful of the Vulcan's greeting. So here you go.
So we're actually going to be talking to a volcanologist who studies volcanoes, not the Vulcan aliens. We should have emailed you that. I'm so sorry.
Oh, my bad. But that's really exciting. So we're going to be talking about volcanoes today. That's great. So for everyone who's joining us, if you have any questions about volcanoes, put them in the comments. And Gavin and Graham, why don't you take it away?
Thanks, Marisa. Yeah, so as we said, today we're having a volcanologist. We are joined today by our good friend and colleague, Seth Burgess. And he works at the USGS, and so we'll be getting into a little bit of his work, the work he did as a graduate student, and the work he's currently doing now. So welcome, Seth.
Yeah, good to be here.
And we should take this time out to say real quick that we might be dealing with some internet issues, so we'll just keep everybody, we'll keep it lighthearted and try to work through that. So Graham, can you get us started today and ask Seth his first question if he's not frozen here?
Yeah, definitely. So we'll give him a chance for his internet to catch up with us, and I'll trust that he's hearing me. One thing I will mention is that you said that he works for the USGS, Gavin, and that is the United States Geological Survey. And so we'll get a chance to ask him a little bit more about what they do.
Seth, are you hearing us, buddy?
Oh, all right.
That was quick.
Yeah, go on, Graham.
Oh yeah, so to fill the time, we can do a quick little introduction just on where Seth is from while he catches up. So I can share my screen real quick.
Give the audience a little bit of background about Seth, what he's doing.
Great, we'll do.
And we're talking about volcanoes today. Are there any volcanoes that are like near us here in Santa Cruz, where all of us are streaming in from?
Not quite near Santa Cruz, but if you drive up north, you get a bunch of them. Lassen Volcanic Field, Shasta, those are all volcanoes. If you drive through Weed, California, you can get a beautiful view of an almost perfect cone volcano. So,
are any of them spewing lava?
Not that I know of, but that's something we should ask Seth.
We'll have to ask Seth, once he rejoins.
Yeah, I don't think there have been any eruptions in California for a while, but that doesn't mean that there may not be some again in the distant future.
Yeah.
Great, but so that sort of gets us to a little bit more about our guests, and I'll just give us a quick moment to go over. So yeah, Seth Burgess, who we'll get to hopefully have a little bit more of a conversation with in a little bit. He works at the U.S. Geologic Survey. They're a governmental agency. And Gavin, within the USGS, what group does Seth work for?
Well, so Seth works for a contingency of the USGS called the California Volcano Observatory. So the USGS comprises of all of like a big branch of the government that employs geologists from a lot of different backgrounds. And so within the USGS, there are some smaller branches that work on specific things. And so Seth works at the California Volcano Observatory. So he's a volcano guy.
Excellent. So a little bit more just about the location of the USGS. So there's USGS offices all over the country. Seth worked at the USG office, formerly of Menlo Park. They actually just moved to some space in Moffett Field. So I'm not sure. We'll have to ask Seth once he's back with us whether they're doing an official name change or not, as they've relocated there. location. There's actually also a USGS here in Santa Cruz, although there isn't a volcano observatory part of that. Gavin, do you know much about the USGS here?
Well, I'm not too versed, Graham, in what exactly they do, but my understanding is that the USGS in Santa Cruz does more ocean sciences and things like that. So because it's so close to the ocean here, they employ a lot of oceanographic sciences, climate science, things like that. And this actually gets me to something, or like brings me to a point that I didn't really understand about the USGS until now, or until like starting grad school. But each USGS office is doing something different. So oftentimes, like say for the Menlo Park, they employ a lot of volcanic scientists, but they don't do the same thing as what the Santa Cruz branch does, and those branches don't do the same thing as the Denver branches. So they're very diverse in what they do.
Yeah, that's right. And it seems that a lot of them, try and keep a focus on the places, something relevant to the regions of the country that they occupy, whether it's water, coastal, volcano, seismology, any sort of thing.
Yeah.
Great. Well, it looks like we're starting to get Seth back on here. I will my next slide is something he can speak to a little bit more. So I'll save the surprise on that. But one thing that we can mention now is that one of the things we'll hopefully get a chance to talk to Seth about is his work with the Siberian Trap volcanoes. So these are very large volcanoes that erupted in Siberia 250 million years ago. And Gavin, we've mentioned these before, right?
That's right, Graham. We've mentioned them several times, and that's because they're really important in geologic history. The Siberian Traps are what caused the Permian mass extinction, which turns out to be the largest mass extinction in the Earth's history. So Seth's done a lot of work on those. And so, okay, I'm seeing something in the chat. Marisa, did you have a suggestion you wanted to say?
Yeah, I think that we want to make sure that Seth can come on in and join us. And since he's having trouble rejoining this meeting, what I propose is that we take a brief break. So we're going to stop streaming for all of you watching with us, but we'll be right back on in a minute. So just hang tight.
All right, Seth, glad you're with us again.
Back. Sorry, guys. Sorry, everybody.
That's okay.
We're still all part of the Zoom lifestyle. So we'll just jump right into the questions. Gavin and I recently got to do some very exciting special access interviews with each other on a previous episode here, and we want to ask you the same question we opened with ourselves, and that is, how did you get into science, and how did you become a volcanologist? And what is it that you do as a volcanologist?
I got into science mainly because I was interested in history and math and physics in high school, and spent my whole childhood outside rummaging around collecting rocks. I had like an Audubon Society guide to rocks and minerals, and I would walk around my folks' property. I grew up kind of out in the country, and we had some space, and I would pick up rocks. And I actually grew up in one of my favorite volcanoes in California, now that I know something about it, the Sonoma volcanic field. It's just north of San Francisco. And so we had lots of obsidian in my yard and Indian artifacts and all kinds of really neat stuff that kind of, even as a kid, gave me this really broad perspective of what history was. And that kind of fired me up. And so I went to college to do it. And I think similar to how most people end up in their, whatever discipline they end up doing, it's just a series of maybe happy coincidences or chances taken, like, oh, I'd kind of like to do that. I think I could be good at that. And it's interesting to me. And so you veer off on that path, and that sort of tortuous path took me to graduate school on the East Coast and then back to California, which is my home state and kind of the area that I love, to work with the USGS on volcanoes. So the childhood interest and then just kind of following that rabbit throughout life thus far has led me to a really fun place.
Totally. And I feel like that happens to a lot of geoscientists. It's like, well, they like to be outside a lot and they've always kind of liked rocks. And then it's like they meander through the world of science until they like take a class on it in college or something. So like we were talking about that with Graham and I last week as well. So it seems as though that's a common sort of thread here. So that's cool, Seth. So, okay, you got the science, you went to the East Coast to do it. You found yourself as a volcanologist out in California.
Mm-hmm.
So how would you describe, like, you call yourself a volcanologist, where do you work? We've already kind of introduced the USGS while you were gone. So can you describe like what the work in the USGS is like?
Sure. So more specifically, well, the USGS is big, and the USGS works on all kinds of different things, from like ecosystems to water resources to the environment, land resources, energy and minerals, things like that. I work specifically under the USGS umbrella of natural hazards. And within natural hazards, there are a bunch of different subdisciplines, from like coastal marine hazards to landslides to earthquakes, and I work in volcanoes. So underneath hazards, I'm in the Volcano Science Center. And within that center, there are 6 different volcano observatories. And our mission is to research and keep the public safe from volcanic eruptions and the things that they cause. So from keeping flight paths safe and people, like international flight travel and commerce, to keeping people that are close to volcanoes safe. And so we do that in the US. And then we also have a little branch that does it around the world. So if a volcano erupts in Panama, we take instrumentation and materials and all of our experience, and we send a team down to help. So that's what the Volcano Science Center does. And a lot of that kind of foundational work to try to prepare us for natural hazards comes in the form of research, original scientific research. So we try to figure out stuff like, how often does this volcano erupt? Does it follow some sort of pattern that we can leverage to tell us more about what it might do in the future? Is it associated with seismicity? When it does erupt, what do those eruptions look like? Are they huge and explosive like, something like Yellowstone would be? Or do they flow over the ground slowly like Hawaii? If they erupt, what's the likely impact to air travel, to people in the area, to tourism, to the industry there, to the water quality, to the animals, all that kind of stuff. So I work on dating rocks. So I date volcanoes, old and young. Mm-hmm. And I do that to try to build an eruptive history of a volcano. So most of the time, volcanoes aren't just a single eruption, like a one-time deal. Most of the time, they're part of a center and they erupt over sometimes many millions of years. And so if we can get accurate dates on all of the rocks that have come out of the ground, we can establish an eruptive history and really inform our hypotheses about what this volcano might do based on what it has done in the past. So that's a big part of my job, is going out in the field, banging on rocks, bringing them back to the lab, which is at Stanford, and getting those rocks dated to as high of accuracy and precision as we can do.
Huh. That's awesome. Okay, so that was a really good I really like that. And so there are a few things that we can jump on. The first thing that came to mind is when you said, like, okay, you work in Menlo Park, but the USGS sends scientists all over, especially if a volcano erupts. And I remember you telling Graham and I that when the recent Hawaiian eruptions a few years ago happened, you went there and worked on that, right?
Yep. Yeah, it was really neat. I got a call to do a 2-week kind of tour of duty. And so we're government employees, and so we're funded by the government to deal with those sorts of incidences. And so we have a volcano observatory in Hawaii on the Big Island. It's in Hilo, where that eruption occurred. It's called the Hawaii Volcano Observatory. And it's the oldest observatory in our little group. And so when that volcano erupted, I got to go over there, and I flew all night and slept a little bit. And the bright and early, like 5 a.m. the next morning, I was in a helicopter flying over those lava flows with a really high-powered camera that was looking at all sorts of thermal imaging of those lava flows. And then I spent 2 weeks living in an Airbnb as close to the lava flows as I could get. And I worked the night shift. So I worked from 10 p.m. to 6 a.m. for 2 weeks and slept hardly none at all. But it was just the coolest thing. That's one of the big perks of the job, is being able to respond to actively erupting volcanoes.
That's awesome.
Yeah.
So Graham, I wanted to see what you thought about this, because last week we were talking about how our science is funded basically through these funding agencies, which turn out to be like taxpayer dollars, but they're through grants and stuff. And so, right, I would think that Seth's work at the USGS, it's a branch of government. It's actually a step closer to actually doing science for public benefit, right?
Yeah, that's right. Yeah, and so you covered some of the things about like natural hazards, and that's a really important thing that the USGS does. And then you had alluded to some other things. So sort of in a general sense, how would you describe the USGS as an entity? And no worries, we're not holding you as the spokesperson for that, but because it is so broad. And for us, me and Gavin are familiar as geochronologists, and so we're like, oh yeah, we get it, like dating volcanic rocks, but it's so much more than that, right?
Right. So the USGS started primarily after the Civil War, before which mostly states dealt with kind of their natural resources. But after the Civil War, there's a big industrial boom, and the government centralized management of those natural resources and sent out 4 major expeditions, like the Powell expedition and the King expedition, Huber. And so in effect, the USGS was founded around managing our natural resources. And that trend has continued since the late 1800s, after its founding, to manage everything from natural hazards to energy and the minerals that we bring out of the earth. All of those things that the government thinks are worthy to have under kind of a centralized agency. And so, Gavin, you guys are both right that the USGS is under the Department of the Interior. So we have a big office out in Reston, Virginia, and we have people, their job is to go to Capitol Hill and fight for money for us. So we say, okay, we think that these volcanoes in Alaska really need to be watched, because many of the air travel routes come over Alaska, especially internationally. And if a volcano erupts, you can't fly through that area. What do you do? And so if we think that we need to better monitor those volcanoes, let's say with geophysics, if one of them is shaking out in the middle of the Aleutian Islands, we want to know. So we have got to get funding in order to take a helicopter to go out there and install that instrument and maintain it. And so we argue for funding from Congress. They appropriate our budget every year. And Congress thinks that it's a great idea to know what's going on with volcanoes and earthquakes as they relate to hazards in the population. And so they argue with the executive branch, the president's budget, to figure out our money. And then we have folks at the top that kind of trickle that money down to the research scientists like me.
Cool. Okay, that makes total sense. It's a little bit different of a setup, but on a day-to-day, you are still doing very similar science to Graham and I, and we've talked to the audience a lot about geochronology, dating rocks, dating. So you do that kind of stuff. And so we were thinking we might take it a little bit closer to home now that you've given the audience like a really good idea of like what the USGS does. Can you talk just briefly a little bit about some of the like California volcano studies you're doing?
Sure.
Yeah.
So California actually has 7 young volcanic centers. So you guys are probably familiar with Lassen and Shasta, Medicine Lake, but there are also volcanoes just east of the Sierras and Mono Lake, right around in there. There's stuff that's just a few hundred years old out there. And Koso Volcanic Field is south, if you know where the Owens Valley is, on the east side of the Sierras, next to a beautiful town called Ridgecrest. There's a young volcanic field down there, and I actually am in charge of a brand new project on the Clear Lake volcanic field, which is the closest big volcanic system, young big volcanic system, to San Francisco and the whole Bay Area population, us and Santa Cruz included. And that volcanic center is home to the biggest geothermal area in the world, the most productive. Yeah, the geysers. And the reason the geysers are there is because there is heat at depth from a magma chamber. And so there's a magma chamber sitting really close to Clear Lake. And Clear Lake itself is built out of a whole bunch of little volcanoes that are as old as 2 million years old and as young as we don't know how young, maybe younger than 10,000 years old, which geologically is quite young. So that's the thing that gets me the fizz right now is about Clear Lake volcano and how future activity in Clear Lake will affect the community that I grew up in and live in now.
Awesome. Okay. So you had mentioned these things are like very similar to the little volcanoes you could see close to the Sierras. So I was thinking that we could show the audience just a picture of Koso. And so I Googled Koso Volcanics. I think we were going to have you show some pictures, but since internet stuff, so I'm going to just share my screen. Oh, Marisa, can you let me share my screen real quick? Okay, here we go. Okay.
See what you came up with.
Okay. So is this, sorry about my icons, but I have 2 pictures up. So is this what you're looking at?
Yeah. So the one on the left from further out. So right in the middle of the screen, you see that kind of a bump?
This one?
With a big flat area. Yeah. So that's a little volcanic. It looks to me like a cinder cone from here. And the one on the right is certainly a cinder cone. That's Red Hill. And you can see that from Highway 395. Right as you walk by, there's a place called Fossil Falls. And it's where a lava flow dammed up this stream. And then you see that Red Peak. And Red Peak is about 75,000 years old.
Wow. Okay. So young.
Got a sample of that, and we dated it in the USGS Argon Geochronology Lab.
Oh, wow. Okay. So I picked the right images off Google Images.
Yeah, those are good. So most of Koso doesn't look just like those 2 pictures, but there are these kind of bulbous high silica domes. So think about squeezing cold toothpaste out of the toothpaste tube. So they come out really viscous and they bubble up into these kind of pimples on an otherwise really flat surface, which is the desert down there, the southern end of the Owens Valley.
Right. And driving past these things, you really can tell that it must be volcanic activity because you're like, wow, that's a valley in there. Look at these, like a ton of little things in there.
Yep. They look like perfect little cinder cones. Yeah, they are.
Right. And I was inspired by your mention of Clear Lake. Gavin, you mind if I?
Yeah, please do.
Opportunity. So can you tell us a little bit about what's going on here?
Yeah, so that is Mount Konocti. And so you're looking across Clear Lake from the east side, looking west at Mount Konocti. And Mount Konocti is a volcano. It's the closest big volcano to the Bay Area. And it was constructed over a couple 100,000 years, from about 500,000 to about 300,000, primarily from dome formation, similar to what we have in Koso, but you get dome after dome and then a flow and then another lava flow, and you kind of build up this edifice. So unlike something like Mount Shasta, which is a stratovolcano, and so you get big eruptions and those lava flows flow down the sides, Mount Konocti and the surrounding little mountains are all kind of big chunks of lava domes that have encroached upon one another as they were built.
Awesome.
Yeah.
That's super cool. Thanks for sharing this stuff with us, Seth.
Sure.
So this is great. This has been fun to learn about some of our local volcanoes, some of our local geology. But Gavin and I also want to hear a little bit more about, like, you know, these volcanoes look big to us, but like these are small potatoes compared to some of the volcanoes you've studied. Would you mind telling us a little bit more about the Siberian Traps?
Sure. So this is work that I did for my PhD, and I did it in this geochronology lab out at Massachusetts Institute of Technology with this really famous guy, Sam Bowery. And he had a lab in which we could date old rocks to higher precision than any other lab in the world. And so what I went out to work on is this thing called the Siberian Traps, which for a decade before my work, folks had implicated in having driven the biggest mass extinction, the most severe mass extinction in Earth history, where like 80% of species on Earth died. And so obviously we want to know what causes such a catastrophic kind of reorganization of the biosphere. And lots of people point to this volcanic eruption. And so if you think of a volcanic eruption on the size of Clear Lake, it is just not even the tip of a pin in volume relative to Siberia. Siberia, the Siberian Traps, as they're called, after the German for stairs, because if you look behind Graham's in his background, those are the Siberian Traps. So you can see all those layers. Each of those layers is a lava flow. So enough lava was erupted in this million-year time period to cover something the size of the entire United States. Like if you look down at the US on a map, something the area of the US over 1 kilometer deep.
Wow.
So let's say half a mile of lava across the whole US. Now you can imagine that liberated lots of volcanic gases, and it also cooked the crust into which it was being emplaced and onto which it was being emplaced. So it generated lots and lots and lots of greenhouse gases. And the geologic record of the mass extinctions suggests that animals were really, really highly affected by an increase in atmospheric temperature and ocean temperature and acidification of the ocean. Pretty much the same thing that we're doing now, but caused not by us, caused by a big volcano. So I set out to date the record of mass extinction and date the volcano so I could see whether or not the volcano started previous to the mass extinction and therefore could have caused it. So I was just looking at their relative timing. And that's what I set out to do.
And you did it well. You have a couple papers on that. So
yeah,
it's still the best geochronology on the Permian mass extinction, I think, right?
Yeah, so other folks in other labs that have kind of caught up to what the lab I got to work in was doing at MIT, they have caught up and they've gone to other sequences of rocks that have preserved the biologic record of the mass extinction, and they have dated horizons throughout that stratigraphic section to as good or even better precision than I was able to get. But you know, that's how science works. Somebody will do something and then other people will iterate on that same theme and really tighten it up. And so that's currently what's happening with the Permian. But no one has redated any of the Siberian Traps. I don't know why. It's such a dreamy place to go do field work.
That's great. So we're a little bit past the half hour, but that's okay. We're catching up for some lost time. And there was one question that Gavin and I could not wait to ask you. And we're guessing the answer to this probably wouldn't be the end Permian. But if you could go to one moment in Earth history, where and when would you go? And then we'd love to hear why you chose then.
Okay, so this is a good question. And I thought about this question this afternoon before we started this. And it's kind of like, you know, when people ask you a question like, oh, if you could go back to one period in Earth history, what would it be? And you'd be like, oh, I want to go see Mozart, you know, play a symphony or something like that. Well, I work on volcanoes. The stuff that I really like to see are volcanoes. And this sounds sort of dumb, But I think the time that I would most like to be in is now, because we have the analytical capability to interrogate the records of these volcanoes, and any one volcanic eruption is not so interesting to me. I really like being able to look at this high fidelity record of many eruptions over time, because it gives you the ability to build like a fully fleshed character out of the volcano. So you really know like what makes that volcano tick. And 20 years ago, we couldn't have done that. Right now, like we're on the leading edge of being able to figure a lot of really neat stuff out that no one's been able to do before. So I guess my kind of lame answer, but well motivated, is that I'd like to be now, but I'd really like to be like 100 years in the future, just to see where the analytical capabilities go, and to be able to learn so much more detail. Like with better capabilities, you can ask so many more nuanced questions of these volcanoes and these systems that we just can't answer now. So I think it's rad to be alive right now, but it would be even cooler to be 100 years from now.
I like that answer too. At first I would have given you a hard time because I'm like,
Yeah.
you wouldn't want to stand in Russia while the traps are, but I think it's cool because it gives the audience sort of a look into how you view a problem. Like you probably couldn't care less about the one cinder cone in Koso that you're dating, but like when you put that little puzzle piece in, you're like putting a puzzle together, right? And you're figuring out how volcanoes work. And that seems to be like a really nice place to leave it in terms of like how you're approaching science and like what your science is motivated by. That's pretty cool.
That is definitely what I wake up every morning wanting to figure out.
So it sounds like it's a great time to be a volcanologist.
That's right.
Yeah, it's pretty good. Right? I mean, there's just so much fun stuff to work on. So I have a wonderful job.
Awesome.
I'd like to jump in really quick because most recently, Seth, you ended on talking about geochronology, and I know that Gavin and Graham, that's your game, yeah. So I'm curious how you all know each other and if you worked together on particular projects, or Gavin and Graham, have you worked within volcanoes at all?
Good question. So Seth is technically our academic uncle. And so the way that works is that our advisor, his name is Terry Blackburn, and he also worked with Sam Bowering at Massachusetts Institute of Technology when Seth was going there. So it's almost like we know each other as a group of colleagues who all work on similar things but different questions. Would you guys agree with that?
Yep.
Yeah, that sounds right. So, not too long ago, Seth and our advisor, Terry, were kind of like the Gavin and Graham of MIT.
That's right. That's right. But to answer the second part of your question, Marisa, I actually do geochronology, but on super different questions. I've never done geochronology on a volcano before. I do geochronology on sedimentary rocks. So it's almost like a whole different geologic ball game than what Seth is working on.
Yeah, that's kind of interesting because so Gavin, you like sedimentary, Graham, you like metamorphic, and so we've now got our igneous geology jet to join.
That's actually a really good way of putting it. Yeah.
I love it.
Geology is so neat because we all work on different rocks and different problems, but in each of those areas of geology, dates are really, really important. How quickly something happens and at what time it happens are universally important. So geochronology is commonly a science that really bridges the gaps between different disciplines.
That's right.
Yeah, cool. Well, I think this might be a good place to sort of leave off. But Gavin and Graham, could you maybe give us a little teaser about what's going on in your world right now and what we'll be talking about next week?
Go ahead, Graham.
Yeah. Thanks, G. So today it was an exciting day for Gavin and I. We are authors on a paper that just got published today, where this whole group of authors. So this was a really fun collaborative effort with a number of people, and we were looking into the timescales of how the Antarctic ice sheet has changed. And so that just came out in Nature, and there was a National Geographic article that covers some of it. So we're very excited. We've all spent a lot of time working on it and thinking on it. So this is one of those exciting moments for us scientists where we can, feel good about the completion of some hard work.
Definitely, yeah. So next week we'll talk about what that paper entailed, and hopefully the museum, I think Marisa will send out a link to at least the National Geographic article. If you just type in National Geographic online today, there will be a story about the ice in Antarctica. So that's our stuff. So we're excited about that, and we'll talk about it next week.
Yeah, I just added the link to the National Geographic article to the comments here. And yeah, it was really exciting to go to nationalgeographic.com and see the article right there on the front page. So congrats, guys. I'm excited to learn more about that. And Seth, do you have anything to share about what you're currently working on, or any exciting news in the works for you?
I'm currently working on getting approval from the folks that do such things to get out in the field in Clear Lake and sample a bunch of rocks out there and get back to work in the lab. We're just getting to where we can get back into the lab at Stanford, where I have an instrument. So that's what I'm really excited about, is putting boots on the ground again. It's been a few months of slouching over my computer.
Awesome. Well, good luck with that. And thanks so much for joining us for this. And for everyone watching for sticking with us. And yeah, Seth, I hope that we can bring you back for more in the future. So.
Sounds good.
Yeah, thanks, Seth.